Hey guys, this is Surya from Skill-Lync. Hope you're doing well. Over the last 6 months, we have introduced something called Premium Internship Program. It's a paid internship for people who enroll in our Premium Master courses. A lot of you had queries about what you will be exactly working on in this internship period. And since it is paid, you had a lot of questions as well. So over the next 3 to 4 videos, what we are going to do is we are going to explain what kind of projects you will be working on in your internship period. As you know, Skill-Lync provides master courses in computational fluid dynamics, design, computer-aided engineering, hybrid electric vehicles, and civil and computer science engineering, right? So we have a lot of domains in which we provide courses. Today, we are going to start with computational fluid dynamics. In this video, we are going to look at what kind of projects you will be working on. This is more of an overview of the projects that you will be working on. Once you enroll and do well in the coursework, you get these internships and you get to work with industry experts who will mentor you during your projects, right? So let's get into this video. And for today's video, I have Sarang with me to explain the different types of projects that you can work on.
Great, thanks Surya. So for this video, what I've done is I've structured the project into primarily these 4 categories, and in each of these categories I will be explaining or giving you a flavor of type of projects that you would be working on. So overall the projects can be broken down into validation and verification projects. So these are projects where you're looking at a paper where there's a well-established flow problem, and you're trying to model and simulate it using your own custom CFD code, or by using a commercial solver. And then the second broad category of projects would be called as application specific projects. So here, what you're doing is we are figuring out popular flow problems across different industries, and what we're trying to do is we are trying to establish a simulation pipeline, essentially a methodology which can be used by engineers to take up a particular thermal system or a fluid system and then figure out how to do the analysis of it in the right way. The third type of project, or third category, is a bit more challenging. This deals with physical models and solver development. As most of you know, computational fluid dynamics is all about solving key differential equations, and when you're doing that, there are several pieces. So you have various mathematical models which represents the physics, but at the end of the day, when you are trying to solve these physical models on a computer, you get a matrix and you have to solve it. So here, one of the interesting projects that you would be working on is solver benchmarking. So when I say solver benchmarking, there are so many different types of linear solvers available for different applications. So here, writing code to understand which type of solver is suitable for which application can give you a lot of insight. And then new physical model implementation and testing. So here the primary agenda is to take up a source code like OpenFOAM and then implement new physical models, and then run rigorous tests to make sure that the model is working as intended. And then finally you have user-defined function development. So this can be used for customized model building, post-processing, and also creating your own input engine whenever you want to read, say, a new data format to do something specific in your application. Now, something that's very interesting but currently which is on hold is experimental methods and verification. As you know, experimental mechanics is a really large chunk of research when it comes to understanding fluid flow, because when you're taking CFD, it just gives you one viewpoint, and that viewpoint is not always accurate. Whereas if you take experimental methods, it's super accurate because you're measuring real fluids and their properties, right? But some of the things that we're working on with a few of our technology partners is performance measurement of fluid systems. It can be a pump, or it could be an IC engine, right? So this is, like I said, still on hold, but once we're able to operate this completely, students will be able to run experiments. They will be able to take realistic data and then take that data, plug it into their simulation model, and do extensive validation. So for this, the type of hardware that you're looking at is wind tunnels and flow benches. The flow bench is essentially an apparatus which can be used to test any type of system you want. It could be an intake port, it could be a centrifugal pump, whatever. All right. So with respect to these projects, currently, we are basically letting students work on validation and verification projects, because these are your intro level projects. And the nice thing is, for all of these different broad areas and categories, we have subject matter experts, domain experts who have tons of experience in computational fluid dynamics, model building and solver development. So you get to work with them directly, and they manage your work remotely. This is amazing experience for any engineer who is just starting out, because currently in your workspace or in your university, you might not have such high quality mentors.
This is all great, right, Sarang? And one of the questions that people ask me very usually is, why should I enroll in a CFD Masters program? Or why should I enroll in an external aerodynamics program? Or why should I enroll in a Masters in Hybrid Electric Vehicle with a specialization in CFD to kind of work on these internships? Can I not directly work on these internships under your guidance? What's your thought process with that? Like, what aspect of our master program enables a student to work on these projects? Say, for example, let's take a canonical flow problem, and let's take analytical model derivation, right? Say if you're an employer and if you're interviewing a student for analytical model derivation, what type of questions would you ask them?
So actually, analytical model derivation might not be a good example to take from a job point of view, but let us say something like a UDF development, right? So for example, this could be for an application engineer role in either a software company like Ansys or Converge, or it could be in a company like Ford or Fiat Chrysler, where the engineer has to take complete ownership of a particular simulation of a thermal system and has to write custom code to do either customized post-processing, report generation, or to add a new physical model that was originally not there. So in that case, the expectation is for the engineer to already be extremely comfortable in writing UDFs, understanding understanding the interface that the software provides, so that you can quickly do your programming and make sure that it works fine. And that's kind of what they expect. And to answer your original question, why do you have to first take up a course and then do this? Well, the short answer is, the difference between learning to walk and running. You have to learn to walk before you can run. So in CFD Masters, you will essentially learn a bit about everything that's mentioned in this particular board, right, except for the experimental part, right? So when a student essentially gets flavors of validation, verification, application specific simulations, and a little bit about solver benchmarking, they are able to tune into the idea, right? And they are able to understand that, hey, this is what I'm interested in. For example, a student, and this has happened a lot, a student might start out with saying that, hey, you know what, I'm really interested in aerospace external flow or aerospace combustion. But when they learn about combustion and chemical kinetics, they might feel like it's mathematically very heavy. There's a lot of programming than they anticipated, and they would say that I don't want to do that. I just want to stick with external flow, and I don't want to write any code. I primarily want to focus on the physics of it, and that's basically it, right? So taking the course in a way helps you understand what is it that you're looking for, and then when you're applying for the internship program, you will know which type of a problem you want to work on. And with respect to an internship, it's going to be much more intensive, right? We're starting out with some really simple problems. A couple of students are currently working on very, very simple canonical flow problems. But then once we get a few more students in, and once they are starting to work with our subject matter experts, the projects are going to be time-based. They have to be able to complete the projects in set time, just like companies would expect them to do, right? So in that case, they cannot be absolute beginners. It's not going to be.
And some of the things that I wanted to ask, so which you touched also, is, say, for example, external flow for aerospace, and that is one of the projects which is, say, Ahmed body, of internal testing on an Ahmed body. Or so, say, if you're taking the Converge external aerodynamics course, there's a FSAE wind tunnel simulation. And one thing that you pointed out is, while these are problems in the assignments and projects that you've solved, so in an internship, there is two aspects of it. In a coursework, you understand the physics, you understand the math, and you understand how to do it. But it is not time-based. Well, it is time-based, but people do not stick to the time. Not everybody. In an internship, it's more of where he interacts with the subject matter expert. Can you explain how an internship kind of works? What is the deliverable from the student? We ask the student to work 40 hours per week, and why is that? What is the deliverable from the student over a 3-month period? What is the output that he can expect out of that internship?
So the idea behind creating the framework for this internship is to essentially give the experience of a full-time job to the student. So most of our students are they're currently in college. Some of them are still in college, right? And the thing that they would not understand is that learning is important, but then at the end of the day, companies hire you so that you can help them finish projects. A lot of students think that they're joining companies because they're going to learn. That's actually a wrong idea. You're actually trying to get a job in a company because you can contribute towards the company's growth, and learning is just a side effect. So essentially, having good theory knowledge and then ability to simulate is just 1/3 of it. But then making sure that you understand the requirements from your boss. It could be a project manager or a technical head, and then breaking that larger project into smaller chunks and achieving that goal, right? I think going through that process and getting that discipline is the primary reason why we have designed this. So students, like I said, currently the internship program is the projects that are being done is fairly basic because we are trying to understand how students are able to manage their time because they are all doing it remotely. But then once we have a good idea about it, the newer students will be working directly with industry experts. So these are guys with at least 15 years of experience working around the world. Now, so this gives the opportunity to the students, to work with someone who is from a different time zone, making sure that email communication is correct, making sure that they show up on time for meetings, and then they make technical presentations to summarize their results on a weekly manner, and then there's a bi-weekly presentation with the technical team at Skill-Lync, right? So when they do this for 12 weeks, I think the amount of discipline that they learn is just huge, and then they not only are able to finish a project correctly in a technical sense, but they are also able to deliver the project in a timely manner.
That's great. Hey, thank you so much for taking time and doing this. So everybody who's watching this is just a part of our CFD Master Program internships, right? There are CFD Masters, Design Masters, Electric Vehicle, Hybrid Electric Vehicle, Civil and Computer Science courses, right? So if you are someone who is wanting to get that industry experience that every recruiter wants, that's what this particular program provides you. The master program provides you the theoretical and the practical aspect of learning and applying it. The internship program allows you to gain that crucial industry experience where you work on a project timeline, right? So we were speaking with Sarang. Sarang himself has around 10 years of experience in computational fluid dynamics. He's our program director for computational fluid dynamics. So you basically end up working with people like Sarang who have a clear idea of what the particular domain is and what the expectation of an employer is from an employee, and that is really crucial, right? So yeah, stay tuned to listen into other internship series, right? But if you're someone who's looking to enroll in a CFD program, this is the right time. Enroll now, do really well in the coursework, and grab an internship as well. Thank you so much.